In section 7.9, we'll predict pressure changes over the course of a reaction in fixed volume containers. Specifically, we'll use Avogadro's law and the ideal gas law to accomplish this task. Let's begin. This is a summary of the stoichiometric operations you're likely to encounter. Notice that the ideal gas law can be used to calculate the number of moles of a reactant or product gas, which can then be used in stoichiometric calculations to determine the mass of a reactant or product. Stoichiometric calculations can also provide the number of moles of a reactant or product gas, which can then be used in the ideal gas law to calculate the pressure, volume, or temperature of the gas sample. Keep in mind that the ideal gas law works only for reactants or products that are in the gas phase. Let's look at an example. This question asks us to find the liters of oxygen produced from the thermal decomposition of potassium chlorate. To answer this, we need to start with the mass of potassium chlorate given, use the molar mass to convert to moles, then use the balanced chemical equation to get to moles of oxygen. We see that oxygen is a gas phase product, so after associating quantities with their respective variables, we can use the ideal gas law, PV equals nRT, to determine the volume of O2. Rearranging, we get V equals nRT over P. Dropping in values, we get V equals 0.01163 moles times the ideal gas law constant times 294 Kelvin divided by 1.13 atmospheres to get 0.248 liters of oxygen to three significant figures. Suppose we're given nitrogen and hydrogen in a cylinder at a certain temperature. When they're allowed to react, what do we know about the system? Let's start by writing the balanced chemical equation. 1 mole of nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia gas. A. What happens to the total number of atoms? The number of atoms stays the same as it does for all reactions. That is the basis for the balanced chemical equation. B. What happens to the total number of molecules? The total number of moles of gas decreases from 4 to 2 as the reaction proceeds, so the number of molecules also decreases by a ratio of 4 to 2. C. What happens to the total pressure? The total pressure decreases as the total number of moles of gas decreases. Since there are only half as many moles of gaseous product as there are of gaseous reactants, the total pressure would decrease to 1/2 of its original value if the reaction goes to completion. We can use what we learned from the last example to elaborate on Gay-Lussac's law of combining volumes. When there is more than one gas in a chemical reaction, the volume ratio of the gases will match the mole ratio of the balanced equation provided the gases are all at the same temperature and pressure. If we invoke the generic reaction, 1 mole of gas A plus 1 mole of gas B yields 3 moles of gas C and 1 mole of gas D, we can say 1 mole of A produces 3 moles of C, or 1 liter of gas A produces 3 liters of gas C. Let's apply this law to a problem. Suppose we decide to heat ammonium carbonate and collect the gaseous decomposition products in separate containers at the same temperature and the same pressure. If we want to know the ratios of ammonia to water vapor, we can use the mole ratio from the balanced chemical equation and Gay-Lussac's law. The ratio of ammonia to water is 2 moles ammonia to 1 mole of H2O. That tells us the volume ratio is also 2 to 1. I'll leave you with the parting thoughts of the authors.